This is lesson 12, our fourth VHDL example, in which we'll design a 2-bit comparator. Now this 2-bit comparator will have 4 inputs, an A1 and an A0, that is a 2-bit A, and a B1, B0, that is a 2-input B. And A can have the value 0, 1, 2, 3, and B can have the value 0, 1, 2, 3. The outputs will be A less than B, A greater than B, and A equal B. A less than B will be equal to 1 if A is less than B. That is, if A1, A0 as a 0 to 3 number is less than B1, B0 as a 3-bit number. If A is greater than B, then A greater than B will be equal to 1. And if A is equal to B, A equal B will be equal to 1. Well, here is the truth table then. We have the 4 inputs, B1, B0, A1, A0, and the 3 outputs, A equal B, A greater than B, A less than B. Notice that A equal B is 1 if A and B are both 0, or if they're both 1, or if they're both 2, or if they're both 3. A greater than B will be 1 if A is greater than B, that is 1 is greater than 0, 2 is greater than 0, 3 is greater than 0, 2 is greater than 1, 3 is greater than 1, and 3 is greater than 2. So those are where A greater than B is 1. A less than B, that'll be 1 if A is less than B. Well, 0 is less than 1, 0 is less than 2, 1 is less than 2, 0 is less than 3, 1 is less than 3, and 2 is less than 3. So that's how we get the truth table. And again, we'll just draw Carnot maps to find the logic equations for A equal B, A greater than B, and A less than B. Let's look at A equal B first. These are min terms 0, and then here's basically 5, and then 10, and then 15. Well, what do we have? Well, we just have the main diagonal. Well, this doesn't look good. We can't simplify anything here, so all we can do is write out the min terms for each of these. So let's go on and look at A. Can't simplify that. Let's look at A greater than B. Okay, here's the Carnot map for A greater than B. Let's fill in the ones. 0, 0, 0, 1. 0, 0, 1, 0. 0, 0, 1, 1. What do we have? 0, 1, 1, 0. 0, 1, 1, 1. And 1, 0, 1, 1. Okay, how many circles here? And we're going to need 3. We have this one, we'll have one up here, and for this one, of course, we can wrap around. So what's this logic equation? This will be not B1 and A1. Not B1 and A1. This one will be not B1 and not B0 and A0. And the wraparound will be not B0 and A1 and A0. Not B0 and A1 and A0. Okay, so that's the logic equation for A greater than B. Let's look at the Carnot map for A less than B. Let's fill these in. 0, 1, 0, 0. 0, 1, 0, 0. Here we have a 1, 0, 0, 0. 1, 0, 0, 0. We have a 1, 0, 0, 1. 1, 0, 0, 1. 1, 1, 0, 1. And 1, 1, 1, 0. And 1, 1, 1, 0. Okay, so again, we're going to have 3 circles. This one, and another wraparound. So what do we have here? We have B1 and not A1. B1 and not A1. Here we have what? B1 goes away, so we have B0 and A1 and not A1 and not A0. And for the wraparound, we'll have B1 and B0 and not A0. Okay, so now we've got the logic equations for A less than B. So we can write our VHDL program. Here's the entity. The input A and B are each 1 down to 0, 2 bits. And the outputs A equal B, A greater than B, and A less than B are of type standard logic. Here's the architecture. We'll just write the 3 logic equations. Remember, for A equal B, we have to write out all the min terms, not B1 and not B0 and not A1 and not A0, and all these 4 min terms. A greater than B and A less than B are just the logic equations we derived from the Carnot maps. Now, here's the top level design. We'll have 4 switches for the inputs, 3 down to 0, and 3 bits for the outputs to represent the A less than B, A greater than B, and A equal B. Again, we have to put the component declaration between architecture and begin for comp 2-bit, and then we'll just port map the outputs to wire it up. A will connect to switches 3 down to 2, B will connect to switches 1 down to 0. We'll make A equal B the middle LED, LD1. We'll make A greater than B the rightmost LED, LD0, and A less than B will set to LD2. Here's the active HDL simulation, and we see that sure enough it works. Notice that we use binary counters for B and A. So we have a binary counter B, which counts slower than A, so that it goes 0, 1, 2, 3, and for each one, A goes 0, 1, 2, 3. Then A equal B is 1 if they're both 0, both 1, both 2, both 3. A greater than B is 1 if A, 1, 2, 3 is greater than 0, 2, 3 is greater than 1, 3 is greater than 2. And A less than B will be 1 when 0 is greater than 1, 0 and 1 are greater than 2, and 0, 1, 2, less than 0, 1, 2 are all less than 3. So the simulation works, and you can go ahead and implement this and download it to FPGA and turn on the switches to see if A equal B, A greater than B, and A less than B light up the correct LED.